Now let's finish our definition of the dot product. It's also called the inner product or the scalar product. We define the dot product for two vectors, u and v, as u dot v is the norm of u times the norm of v times the cosine of theta, where theta is the angle between the two. Most of the time, this is the physics definition of the dot product. For us, we're going to use the component-wise definition. Okay, here, if we have u as having coordinates a, b, and v as having coordinates c, d, then u dot v is going to be, let me write it here in this manner, ab times cd. So here we're going to do the component-wise. Okay, we're going to have ac plus bd. Okay, so this is for the case when the vectors are in V2, the set of vectors in R squared. Okay, this is what we do here. So we multiply the x components and the y components, and we add them. Okay, this is the definition that we're going to need to prove many results. Okay, this is very useful. It's very important in physics when dealing with moments, and this is the definition that we're going to use over and over again. Okay, for instance, we can use this one to find the dot product of u with itself. Okay, in this case, what we have is AB dotted with AB. And in this case, we have a squared plus b squared. And according to this definition here, we have u, the norm of u, times the norm of u, times the cosine of theta. And theta in this case is 0. Therefore, the cosine is 1. Here, this is 1 because theta in this case, it's the angle between u and u, which is 0. Okay, and therefore here we have u dot u is the norm of u squared. And in this case, we define the square of a vector as the square of its norm. Okay, very critical and very important. So here we're going to use it. Okay, sometimes we use another notation for the dot product. uv is going to be something like this. Okay, here we're going to use the component. Okay, so if we assume that u has component ab, and if we have an orthonormal basis, so u and v are in some orthonormal basis, then u can be written as a e1 plus b e2, and v can be written as c e1 plus d e2. Okay, so let's say this is my u, this is my v, and this is my system, coordinate system. Okay, u and v are written in this coordinate system in the following manner. And therefore, I can use one key idea here, is that the dot product of E1 with itself is 1. We see why. If we apply the definition here, so we have, this is just the dot product of E1, the vector E1 with itself. So it's going to be the norm of E1 times the norm of E1 times the cosine between E1 and E1, which is 0. And this is just 1 because this is a unit vector. So we have 1. The same thing for E2 with E2. Okay, it's going to give me E2 with E2, which is 1. The key here is that when I do the dot or the the scalar product of E1 with E2. What do we get? You get the norm of E1 times the norm of E2 times the cosine of theta. Theta is the angle between E1 and E2, which is pi over 2. Therefore, I have 0. So now I can use this notation here and go back to where did I put it? Here, and get this result here. Okay? So we can do it here component-wise using these facts here and find this result here. Okay? So using this fact, and if we distribute, we will have all the result that we need. One key idea that we didn't mention is that the dot product of U and V is the same as the dot product of V and U. Using the definition, from the definition we see that this is possible. Okay. Thank you very much.